the there's someone from IT named Thomas uh, Hollister, and so um, Masoma, Deja, and Corey, I think, do not have access currently, and they need to reach out to him. I sent an
Yeah.
email
Hmm.
with his phone number. Um, but I think everyone else has access. Jadifi, can you access the cluster? Yeah, and Aaliyah can.
Yeah, you can proceed.
Aaliyah, can you access the cluster?
Me?
No, Aaliyah.
Okay. Alia, can you access the cluster?
Haven't checked, but
Can
I
you
can
say that
check it
again?
now. Yeah, I said I haven't checked, but I can check it now.
So they'll get back to me later today. Okay. Yeah, so just contact Mr. Thomas because it's on, TSU's side. It's not, I don't think it's any of your fault. Um, okay. So yeah, we'll go on to the subject of today, which is molecular docking. Everyone can see my screen. And so today, let me put my laser. Okay. And it's not advancing. There we go. All right. So molecular docking is a computational method for predicting interactions of molecules. And so these can be small molecules, we might think of as drugs with proteins. You can also do proteins in other proteins or peptides in proteins. But so this is a use of algorithms to search for the most energetically favorable interaction or positioning um, of, your target molecule and then giving it a score. And so this is commonly used in drug discovery um, to search for small molecule ligands that interact with a target protein, such as a receptor. This is what we call computer-aided drug design. Like I said, also can be used for other interactions, such as protein-protein interactions. As far as the software involved, there's a lot out there. They differ in their algorithms, scoring functions, user interfaces. Most are free, but some of the more advanced, kind of user-friendly ones are commercial, which you have to pay for. Um, some of the free software include Autodock, Doc, Haddock, or Protein Protein. Some of these offer web server interfaces, which are easier to use, where you can just kind of upload your structures and submit it to the server. But most of the free software is command line interface, right? So it'd be like Linux commands. And so, docking is a form of structure-based drug design. And when we say structure, we mean the target structure, like, the receptor, what we're trying to bind a drug to. Um, and this is opposed to ligand-based drug design, where we already have known drugs and we're trying to kind of modify them, change them up a little bit to make them better drugs. So that would be ligand-based drug design. And as far as these structures that we're using, proteins, nucleic acids, DNA, RNA, we get these using a couple techniques. One of them is X-ray crystallography. Most of the structures that you'll see are, determined with the X-ray crystallography. There's also a newer method, cryogenic electron microscopy or cryo-EM. This is gaining ground. The technology is improving. The and it's becoming more popular, and it's better at getting like larger structures where you have many maybe different proteins interacting together. And so this, molecular docking can also be used to screen, large numbers of compounds, what we call high throughput virtual screening. And this is basically, we have, anywhere from thousands to millions to now we're doing billions of these, small molecule drugs, and we're just kind of like docking them really quickly and trying to find some that, work. And so this is just like an outline of X-ray crystallography and then cryo-EM, the methods. And so the typical protocol for a protein ligand molecular docking would be to, get your protein, prepare the protein. This includes removing water and ions and other what we call heteroatoms that are not associated with the protein. But sometimes we want to keep some, so maybe there's a cofactor like zinc or a coenzyme involved, and that being present will actually help a more realistic docking situation. We also need to add hydrogen atoms because these are not resolved in the structures from X-ray or cryo-EM. They're just too small of atoms. And the next step will be to prepare our ligand. And so we also need to add hydrogen atoms. We need to also determine which bonds are rotatable, and right, because our ligand can rotate in order to form bonds or conformations in the receptor or protein. We also have to figure out where we want to target on that protein. So this would be our binding site. Um, Maybe we have some prior knowledge. We know where our binding site is already. There's also ways to just use, algorithms to determine an optimal site based on the certain atoms there and what are likely to bond to it. And we also need to, figure out how big of a size we want to search on that protein, because that can, speed up our process if we narrow it down. As far as protein structures, and so these can be acquired from the protein data bank. It's rcsb.org, and there are currently over 200,000 structures available. And each structure has its own page and has background information, the number of atoms, the journal article that was associated with it, and information about the protein. As far as chemical structures, such as our small molecules, there's the Open Chemistry Database at the NIH, which we call PubChem. There are other databases out there as well, but PubChem is a good one. It's well annotated, or it has a lot of data around it. And so here, this is where I would start, showing you how to do the actual docking. And for those of you who can log on, try to follow along. This is also recorded, and I'll share the slides with you in case you're having trouble. But so, go to your home directory, create a new directory. And so I'll just briefly go through this, and then I'll do it in real time. Called docking, right? We want to be organized. We have a lot of data. We want everything to be situated in its respective folders or directories. Here we're going to use Linux desktop app because everything's all the programs, run through Linux. And then, only need 4 cores. If I was doing a larger scale kind of screening, I would, want to use probably all the cores in the GPU. And launch your desktop when it's running, when it's ready. And then if your web browser is going to pop up this, just allow so you can copy and paste. It just makes life a little easier. And so this is what your Linux desktop terminal will look like. We have our terminal emulator down here, little button. And so, I need to find a protein, target. And so, I go to the protein data bank, the website. So this is the website. And I'm just kind of doing some background, investigation. What kind of protein? What's the PDB ID, which I can use, to download the structure. And so here I picked GAPDH because this is one of the proteins that we're working with, with the Department of Energy and their project. And so basically, what I need here is, this 6M61
Dr. Scott, I'm so sorry. I didn't mean to interrupt you, but my
Oh yeah.
computer had died.
Uh-huh.
So do you want me to just follow along?
Yeah,
Because
yeah.
I'm
Just
okay.
pay attention.
Okay,
And
sorry about that.
like I said, we're recording this, and then I'll give you the slides as well. So I tried to make it as detailed as possible, so you can, follow along. I have all these arrows kind of pointing out which buttons to push, all this. But yeah, once we have our structure, our PDB ID, we can actually just download it through, the Linux desktop. And so I chose this one because the structure on the PDB is complexed with an inhibitor, what they call F4F. And, here's the chemical formula. And so this is really not going to help me as far as, downloading the structure through the Linux desktop. So I need to go to PubChem. I just copy and paste that formula into the search bar, and I start my search. I can find some results, and so this one came up with 2 results, and this top result actually has a sulfur atom, and which if I look at the structure that was deposited on the PDB website, it doesn't have a sulfur atom, and so I'm gonna go with this one below it that doesn't. That's pretty much the same structure that they said it was on the PDB website. And so from here, I need this compound ID, CID, right here. So I'm going to make a note of that. And so I can actually download this molecule from PubChem using Python, using a package in Python. And so first I'll need to install the package. And so, this is on the terminal emulator, right? That button on the bottom that I was showing you earlier. If you push that button, it's going to pop open a new terminal like this, and where you should be able to type in commands. And so this first command is going to be module load Python, because I need to actually load the Python program first. And then I'm going to do, if you remember from our Python tutorial, I'm going to use pip, which is the package installer for Python, and pip install this package pubchempy. And so somebody made a package that allows you to download, directly from the PubChem website, while you're in Python. And so it does, some downloads and installs it, and then what we'd like to see is this successfully installed, and we're good to go. That package is installed. And so now we can, once we have that package installed, now we can download the compound. And the format we're going to use is the 3-dimensional SDF format. This is just a common format used for, small molecules. And so I'm going to change directory into that docking folder that I created earlier by just typing cd docking and then hit enter. And then if you see here, this changed to docking, which means that I'm currently in that docking folder. And then I'm going to just type the word Python, which opens the Python program. And then you should see this, this right here. And then these 3 arrows, this tells you that you're in Python, right? You're no longer in the Linux kind of language. And so here, if I type from pubchempy, which is our package, import download, which is our module. You remember from our Python tutorial, there's packages, there's modules and submodules. But really all I need is from this package is this download module. And so once I do that, I can use it by just, and so this these parameters, or these called arguments, I had to look at how to use the package, which is on the website. So if I just search for pubchempy, it'll take me probably to one of the first results on the search would be like the Python package repository, and then it gives me information about the package. And so in this line right here, I'm using the download module, and I'm saying I want it in SDF format. I want you to name the file as f4f.sdf. And then this would be the compound ID that I got earlier from the website. And this is telling it I'm using the compound ID. And then I include this record type 3D because I want it in 3D format. And once I do that, nothing, it shouldn't show anything like successfully downloaded or anything. It just, if there's no error, then your command successfully ran. And then so once I've downloaded it, I just type quit, open close parentheses, and hit enter, and then it exits out of Python. And now you can see I'm back on, in the Linux mode.
Hey, Dr. Scott, this
Yeah.
might be a crazy question, but is this like almost the same thing as like coding?
Yeah. It's essentially coding. Yeah.
Oh, okay. Oh, okay. Sweet.
Yeah.
You started coding from Linux, don't you know?
Yeah. So Linux and Python are 2 different languages, right? And so when I'm working around the cluster and like organizing my files, I'm using Linux. When I using the Python program, it's a different syntax. It's a different language, right? Okay, and then so once I have my my molecule downloaded, I'll need to convert it to another format, which this Autodock program uses. And so here I'm loading OpenBabel, which is a format conversion tool, very useful. And then the command to convert to that new format would be obabel, and then the original file name, and then dash capital O, and then the new file name and format, right? So I'm converting it from SDF to PDBQT. And so this will actually tell me 1 molecule converted, and that's all I needed to do with that. And then as far as the protein, we can download this through our Chimera X app. And so once again, I'll have to load the app. And so I'll do, and so this is, remember, this is in Linux. Module load Chimera X. And then if I just type Chimera X, it will open up the program in a new window. And from here, I can open or download or fetch a structure by going File and then click on Fetch by ID. And then this little window will pop up here. And then I want to make sure it's highlighted on PDB because that's the the code I have. And then if I enter that 6M61, the PDB ID down here, and then I click fetch, it will download the structure, protein structure. And so here it should automatically pop up. And so this is telling you that it downloaded from the PDB, what the protein is. This is the title of if we go back to the PDB website, this is the title. It tells you the different chains of the protein, and then non-standard residues, such as our ligand here, F4F, some other ethylene glycol, NAD, a zinc ion, stuff like that. That's not, protein. And so I don't want all of these chains because they're basically, this is like a tetramer, right? It's 4 copies of the same protein. And for docking, I only need 1. And so here I'm going to select 3 of the chains that I don't need. And so down here, I'm going to type select and then /PQR. So remember, these are my chains. I'm only interested in O. So I'm going to select PQ and R, and then it'll highlight them all. And then I can go to up here at the top, actions, atoms, bonds, and then click delete. And then it will delete all those extra chains that I didn't want. And then, so we're left with our chain O. And
So the ones that you want to delete, you're going to type those in. The ones that you want to keep, you're going to leave that out, basically.
right, yeah. So I'm
Okay.
selecting all but the one that I want to keep because I'm just going to, why I'm selecting them is to delete them. Yeah. And once you get here, you can use your mouse or your pad if you're on a laptop. And so your left button, if you hold it down, would rotate the structure. If you hold the right button on your mouse, it'll actually just kind of move the whole structure up, left, right, up, down. And then your wheel on your mouse would enable you to zoom in or zoom out on the protein. And so we can change the colors, of different aspects of the structure to better see. Yes, Jadivi, you raise your hand.
I'm sorry, I keep asking all these questions, but what if I don't have a wheel on my mouse? Like, how would I zoom in and out?
You zoom. I think maybe if you can hold control down and then move and then use the left. I don't know.
Yeah.
There's a way, I think, without the wheel.
Okay. Thank you.
Or like pinch and zoom kind of thing. Yeah. And then so to change colors, I can go to actions, color, and then if I wanted everything to be one color, I could pick one of these. I could, but if I go down to the all options, I can get a little more specific, and then I can this has an arrow missing. There we go. I can click by polymer, and it's going to automatically kind of color each distinct, chemical entity a different color. And so here my protein's all in blue. my ligand of interest, oops, is right here. And then this is NAD, which is a coenzyme. And then these little red dots are water molecules or solvent. This one might be that ethylene glycol. This big, dot right here, that's a zinc ion. And so when you color everything by different colors, it's just easier to make sense of it all. And then so here I'm going to save this structure as it is for comparison to the docking results. All right, so I'm just going to go File, Save. There's also a button on here that says Save as well. Basically, I'm going to save it as the original. So I'm going to give it a name .pdb, and just hit save, and it's going to save it in my docking folder. Okay, now that we have that saved, we need to continue cleaning up the protein. And so if I go to select and then residues and then all non-standard, right, which includes my water, my ligand, and all the other things, it's going to highlight all of those, right, shown in green here. And then I can just delete those like I deleted those chains earlier. And so I just go to Actions, Atoms, and then Delete. And once that's done, I'll have a clean structure, but I'll still need to do some preparing. Luckily, Chimera has this handy tool called Doc Prep that pretty much takes care of all that for you. And so just go to Tools, Structure Editing, and then Doc Prep. And then a window is going to pop up, and you can just keep everything for the default settings and just click OK. And then another window will pop up for you to add hydrogens, and then you can just keep everything in the default mode and hit OK. And it's going to assign charges to your protein, and just hit OK. And once that's done, like down here, it should say like doc prep finished. Then we can save our, prepared clean protein. And so I'm just going to save it as, the name, the title 6m61.pdb, and just hit save. And I'm done with Chimera X now, so then I can just, exit by doing File and then Quit. Okay, so we still have to convert our protein structure to the PDB-QT format like we did our ligand or chemical. And so here it's a little bit different. We're going to use the Autodock tools or suite. And so I need to load this app as well. So I'll do, on the command line, module load ADFR suite. And then once that's loaded, I can use this command, prepare _ receptor, and then -R, which is for receptor. And then I'm going to type in my, the clean structure that I saved. And it's going to add some charges to the peptide, and it converts it to the PDB-QT format. And then if I, do the ls command to list whatever in my directory, I can see that it created this new file. And so now that I have that converted protein structure, I need to determine a binding pocket. And so I can do this with AutoGrid, which is part of that Autodock tools suite. And so if I just type this AGFR GUI they actually have a graphical user interface, or GUI, which will pop up. And so once this, you type this in, hit enter, and then this will pop up. And then you can select your receptor by hitting this button, PDBQT. It's going to open up a file window, and then you can select your PDBQT protein and hit open. And here it's going to calculate what they call affinity maps, right? Where it kind of uses an algorithm to go through all the atoms and determine what's the best site on this protein where a chemical would like to bind. And so when I hit this compute pockets button, it's going to this green area should show up, which is our top scoring pocket right here. And if I want to just kind of zoom in on that, I can hit this button right here with the orange balls in it. And it's going to kind of zoom in on that binding pocket that's determined to be the best spot. And then I need to generate some files. And so if I hit this generate target file button down here on the bottom, it's going to open up a new window, and it's going to ask me to save the name of this. So I just put 6M61, and that's just hit save. And it's going to take a few seconds to create the files. And then when it's done, it's going to say generated target file. And then I am done with AGFR. And so I can just hit the X button up here to exit. Okay. So I have my target file, and then so what's in this file is that atom types, the what they call the box, the dimensions of the box in 3 dimensions, the size of the box. And so all we really need from this file is the center coordinates of our box, and then the size. And so these are in X, Y, Z. And so we just need to remember these numbers. And so the way I got to this file is I just typed about, and then the name of that file, that target file that we saved, and it automatically bring up this this file right here. And so I need to use those coordinates and the size of the box, and I need to create a configuration file for my docking software. And so here, it's easier if we just open up a new window, right, and kind of just copy paste from that target file. And so if I click on that terminal emulator button again, it's going to open up a new window. And I could just move it to the side. And so in my original window, I type that command about, and then the file name, and it's going to open up that file again, the target file. And in my new window, I'm going to go to my docking folder first, and then I'm going to type this nano conf.txt. And so what I'm doing here is Nano is a text editor, and it's creating a file called conf.txt. And so when I type in nanoconf.txt, it should open up, oops, going the wrong way. Should open up the text editor. And up here it says the name of the file that we created. And so this is, I have to type all of this in. And see, I'm getting the center X, Y, and Z values from here, X, Y, Z. I'm getting the size of my X, Y, Z from here, 44, 52, and 44. You don't need the preceding zeros here. And then I'm including this exhaustiveness command right here for 32. And so this just increases the sensitivity of the docking. Okay, and then once I have that all typed up in my new file, I'm going to type, and so here I'm just showing, this is both the same window, right? This is our conf.txt in our text editor. And so to save it, I'm going to hit Control plus O, right? Hold down Control and hit O, and it's going to, that will save your file. It's going to, down here, it's going to say file name to write. It's just confirming that this is the file name. And so if I just hit enter, it will save the file. And it's going to go back to kind of this format. And then, to exit, once you've saved the file, to exit, you can just hit Control X and it should automatically close out the text editor. Okay, now we've got our proteins ready to go, our chemicals ready to go, and our configuration file, which makes it easier. We don't have to type in all those different parameters. It's all in one file. And so to run the docking, I module load Autodock Vina. So this is a popular free docking software. Once I've loaded it, I can type Vina and then -- config, and then the name of my configuration file that I created, conf.txt, and then just hit enter. And then it'll start processing your docking, and it'll take a few seconds, and then it's going to show you results right here with different docking scores, RMSD values, root mean square deviation values. But what we're most interested in is this affinity in kilocals per mole. And then it should say writing output done. And then so it's going to create an output file, which is this f4f underscore out.pdp qt. And so this contains all of those different poses, right? So these are different poses of the way the molecule is in 3D space within the protein. And to look at that, we can go to our Chimera X app again. And so first we need to unload that ADFR suite that we loaded previously, because there's a conflict with the Chimera X app. And so first I want to unload ADFR suite, and then I've already had Chimera X loaded. And so I can just type Chimera X and hit enter, and it should pop up again. And here it's just showing some of my previous files that I've been, playing with. And if I go to file open, and then I click on my F4F out, which is my docking results, and then open, it's going to show all of the poses all jumbled together, which is not useful for us. And so if I click this check mark right here, it's going to deselect all of them. And then I just click on the first one. It'll just show that first pose that I'm most interested in. And from here, so I just have the chemical, but I want to see how it looks in the receptor. And so if I open up that my receptor, which is the 6m61.pdbqt, the same way file open, it'll load the protein, and then this is where my my chemical is within the protein. And so this is what we call our complex of our inhibitor F4F and the protein GAP-DH. So within Chimera, there's a binding analysis tool called View.x. And so you can go to Tools, Binding Analysis, and then View.x. And then some information on the right will pop up. I can look at hydrogen bonds if I, type or click this button. Hydrogen bonds are important for ligands. This is what we look for strong. These are pretty strong bonds as far as a small molecule and a protein. So we like to see these. So remember I saved that original file because I want to see how my docking looks to the original X-ray structure that they determined. And so if I just keep everything there, and I can add to that, the docking results. If I go to File, Open, and then open that original one that I saved, and it's going to overlay onto my docking results. And so I colored the F4F original in red, and then NAD in yellow, and then our new docked inhibitor is in tan right here. And so you can see that the positions are not the same, and so it looks like they're this would be clashing with this NAD molecule that's present. And so what I did is using that information, I redocked. I kept the NAD in the protein, and then I redocked it, and then I get a much better position that's nearly identical to the original PDBs. And so this brings up the point that, context matters, whether it be your kind of like your zinc ions, your cofactors. NAD is a important coenzyme for this GAP-DH protein. And so, yeah, just showing you that sometimes you don't want to remove everything, right? Because this NAD here was kind of determining the position of how that inhibitor would bind to the protein. Okay. And yeah, so that's protein ligand docking. Simple. I know my protein and know my ligand. Let's dock them and see what's the the best position on the protein where this would fit. And you can dock your own molecules now. And so like I said, I'll share those with you. And just to show how you can do that, I will let's share my okay. You guys can see my screen again. Okay, so here I'm on I've opened up an incognito tab in Google Chrome. The reason I do this is because I switch profiles sometimes and it removes the cookies. And so, but for you, you don't really need to use an incognito tab. But I would go to biorack.tsu.edu. Right. I created a Brave training profile. And so to look at my home directory, files, home directory, I already created that docking folder right here. But if I wanted to, just go in there and see what's in there, I could just click on it. It'll take me in there. If I want to go back to my home directory, just click on that. And then so to get a Linux desktop, interactive sessions, Linux desktop, 4 cores, 2 hours. I mean, it depends on, how long you need to work. You can change the amount of hours. hit launch. And it's going to take a few seconds. There you go. And hit launch desktop. Okay, and then here this is my Linux desktop, and then here's my terminal emulator down here. And so, I'm in my home directory. I need to go to my docking directory, COD CD docking, and there's that tab autocomplete. So if I just type dock and then hit tab, it'll autocomplete docking for me. And so here I'm in my docking folder, and let's see what I do first. Module load Python. And so to enter Python, just type Python. And then it says Python version 3.11.2, to I guess when it was installed. And so this is Python, and I have if you're going, you have commands that you've used previously, you can hit the up arrow, right? And it'll kind of scroll through your history. And so they're from pubchem import download. I think this might give me an error because I already downloaded it. Yeah. But so yeah, the reason it's giving me an error because it already exists. If I want to overwrite it, let's see. Yeah, and so if I just overwrite it, then there's no error. So there I just downloaded the compound, and so if I just want to quit, open close parentheses, and then it exits Python. And so I think the next step was open Babel. Remember, let's see. Yeah. Okay, so I need to load my open Babel app. And if I do Babel, what is it? Right. Converted that SDF to PDBQT. And I'm done with that. And so if I want to go to Chimera X, just type Chimera module load and then the name of the app, and then it's going to pop up. And if I want to, fetch that PDB, make sure it's highlighted here. 6N61. And it's pretty quick, pops right up. And there's my and so here I'm rotating. I'm using my left mouse button to rotate, right mouse button to kind of like strafe, left, right, up, down. Zoom using my wheel. Um, let me see if controlled. Yeah. So as far as without a wheel, I'm sure there's a way to do it. Yeah, and then so to color by polymer. Oh, it's taking a while because I didn't delete all those other chains. Let me delete those. I think this has history on it too. Yeah. So I just typed up arrow and it went to my history of my commands down here. Oh. And so it selected P, Q, and R. You can maybe see that this portion is not highlighted. Just gonna delete those. Actions, color. bipolymer. Right. Okay, and there's my inhibitor right there. It's that like bicyclic, like 2 rings. And then this is NAD, and then all, the solvent or water. And then I need to remove those. So I want to select if I go to residues, all non-standard, and then actions, atoms, delete. And there's my, protein without any other atoms in there. Right. And if you want to look at sticks, so let me select, maybe I want to see like all the different, all the different side chains of the amino acids. Like you could do that if you wanted to. But then the important thing here is to do the doc prep, right? Tools, structure editing, doc prep. Just keep the default values there. Just keep hitting OK. And doc prep finished. And, I would save it as a PDBQT. And so once I'm done with Chimera, I need to convert that to a PDB QT. And so module load ADFR suites. Right. I'm just doing the tab complete all the time. Makes life easier. Right. So I just converted the PDB to the PDB QT, which would be right here is my new file. And if I do AGFR GUI, this is going to pop up, right? And all this is pretty quick. There's really not much lag, and right. So this is all right, forwarding to my computer from our server, which is located in the IT office in Hannah Hall. And so click PDBQT, right? I'm clicking my receptor 6M61, and it should pop up. You can actually, play around with this as well with your mouse. And so if I compute pockets, it's down here, it's kind of showing what it was doing. Now it's ready to kind of pick that first pocket right there, which it determined was kind of the best area for a ligand to bind, and then hit generate target file. And then, once it's complete, it'll say generated target file. And I can just exit. And now I need to, if I do about that target file, it's going to pop up all this, and I can, increase the size of my window so I can see everything. But yeah, so, the name of the file, here's our important information right here, center and size. Okay, and then so if I do the nano, which is my text editor, and then my conf.txt, this is my configuration file, right? And so receptor, my PDBQT of my protein, 6M61, my ligand equals that inhibitor F4F, and then I'm entering in the coordinates and then the size, and then this exhaustiveness command. Once that's done, I can hit control, hold down control and hit the letter O, and see it pops up right here. I just hit enter and that goes away, and then I just hold down control and hit X, and then it exits out of the text editor. Okay, and now I am ready to run the docking. So I need to unload that. Is it? No, do I need to? I don't know. Let's see. Module load Autodock Vina. And then see if I have it pretty close here. Just scrolling through. Okay, no, I don't. I'll have to type it out. Vina, what is it? Config, and then conf.txt. Just hit enter. And then just, it takes about 10 seconds to go through. And so, here it's just kind of like rotating the molecule, rotating the bonds, and kind of figuring out what's the optimal position. And there it's done. And then, I can go to Chimera. Let me unload that guy, module unload ADFR suites, and then open up my Chimera X. And then if I do open, remember this out is my docking results. And then you get this jumbled mess of molecules. And just type, hit this button right here, and they all disappear. And then just take the first one. Right, and so that's my 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 ligand, and then I can open my receptor 6M61. Let me see. Oh, and then I can
So when
open up.
you, yeah, okay. So on the 6M61, is there a specific one that you're supposed to choose? Because I noticed there were 3 different ones.
Yeah, you can just choose the one that I used for docking, which is the PDB QT.
Okay.
I can try the. Yeah, so that's the PDB form. It's the same. You can see it. It's overlaid, and it's kind of trying to show both of them with the different colors. But either one would work. Yep, and see my original. And so that's with the original. Okay, yeah. And then yep, just hit X to exit out. And that's about it. So you guys should be able to replicate this. I've tested it out many times. It should work for you. Just follow the directions. So please, everyone, try to do this. And so once you've done that, if you could yeah, let me know that if you're having trouble, please reach out and I can help you troubleshoot. There's some problems. And feel free to dock your own proteins. Maybe you want to look at like COVID, maybe some COVID inhibitors or something, a protein from the virus. Yeah.
Do you mind if I like stop by your office sometime next week, like just to like go through it? Because I feel like, I mean, it's available to me. I just want to make sure that I'm like properly going through the steps, because the slides I went through, I don't know where in which I was getting confused, but it wasn't looking like your slides. So
Yeah,
I
yeah,
don't mind coming up there.
yeah, for sure. Yeah.
Okay.
Aaliyah?
Yeah, so I tried logging into the website.
Mm-hmm. You got in?
And no, like the
Oh.
VPN has issues.
The VPN's not working?
Yeah, it says that the network is transferred into an alternate network. And when I used to put on the VPN in the past, it doesn't act like this.
So it was
When I
working for
tried
you
to,
in the
I
past.
mean, I was able to log in to the VPN with my CSV email and password. But then after I logged in, it told me that it transferred me to another alternative network. And after I saw the message, I tried logging into the BioRack cluster page, but it's not open. It says server IP address cannot be found.
Mm, okay. Yeah, I guess where are you right now?
I'm on campus.
You're on campus and you're on your laptop?
Yes, I'm using TS2 Wi-Fi.
The
TS2
TSU
student.
student?
Yes.
Okay. Yeah, it should work. Yeah, I don't know. We'll have to like troubleshoot it. You'll have to either come here or reach out to the IT guy, Thomas, because it should
Okay.
work. Yeah. Yeah, just give me an email heads up before you head over.
Okay. I want
Doesn't
to
have to
try
be
it
today,
again.
but next week or
Okay.
whatever. Yeah.
And the slides will be sent, right?
Yes.
Okay, thank you.
Okay. Corey, are you able to connect?
I'm about to pull out my computer right now. I was on my phone. So just give me like 5 minutes and I'll get back to you.
Okay. All right. Well,
But Dr. Scott, I actually have to get ready for work. Did you want me to stay around for a little bit?
no, no, no. I'm done with, lecturing. I just want you guys to try it out on, on your own time, and then just if you have trouble, just reach out.
Yeah, I just posted the message I see whenever I turn on the VPN in the chat.
Reliable.
Dr. Doe, am I free to leave? I don't think he's there.
Yeah,
I don't
yeah, yeah.
I
You
don't
can
want
leave.
to get in
It's
trouble or
fine.
anything, but
No, yeah. No, you're fine. Yeah, it's okay.
all right. Well, I'll message you sometime next week to like come in and then we can like just assess it. But over the weekend I'll try to like configure it and see if how far I can get.
Yeah, yeah. Just practice. Yeah.
Okay, thanks again. Have a good day, guys.
Yep. You too.
Dr.
Bye,
Scott,
guys.
is it fine if I can go over there right now? My computer's actually dead.
If you can come
And
over to the
yeah,
office.
yes, sir. I'm in Hannah right now. Is it fine if I
Yeah.
could pass over there? Okay,
Yeah, that's fine.
I'm on the way.
All right. Thank you, Scott.
Yep.
You guys should have a
Okay.
great weekend.
Aaliyah, yeah, let me forward that to the IT guy. I think it's just has something to do with the network, like the signal. It's not.
Maybe TSU student network is
Yeah, I
poor.
know it's not the
That's
best.
why.
So yeah, can you try if you can try at home on
Okay.
your home network? Yeah, cool. All right. Mm, Masoma. Yeah, Masoma.
Hi, Dr. Scott. Oh,
Hey, you are
like I
you
said,
reached out to Thomas?
yeah, I did. I
Yes.
reached out
Okay.
to Thomas and he said he would give me a call back before the day ends. And
Okay.
then we try to see if he can fix the accessing the cluster problem.
Okay. Yeah, great.
That's the only updates I have.
Yeah. I know he's busy, so
Right.
it might take a
Yes.
while.
Yes.
Okay. Sounds good.
Thank you, Dr. Scott. I'll see you later.
Okay.
Have a good one. Have a great weekend.
You too. Take care.